สวัสดีค่ะสวัสดีแขกผู้มีเกียรติทุกท่านนะคะเรากลับมาเจอกันในช่วงเวลา 15:15 นาทีโดยประมาณค่ะซึ่งสำหรับในช่วงนี้ค่ะท่านไหนนะคะที่สนใจเข้ามาร่วมฟังนะคะสำหรับในหัวข้อสัมมนาสำหรับในเซสชันนี้ค่ะเรียนเชิญนะคะทุกท่านค่ะสามารถมายังบริเวณด้านหน้าเวทีได้เลยเพราะเดี๋ยวอีกสักครู่หนึ่งเราจะเริ่มต้นขึ้นแล้วนะคะสำหรับกิจกรรมการสัมมนาซึ่งแน่นอนว่าอย่างที่หลายๆท่านได้ทราบกันดีแล้วนะคะว่าวันนี้เนี่ยเราก็จะมีทั้งหมด5เซสชันด้วยกันค่ะซึ่งเราดำเนินมาจนถึงในช่วงของหัวข้อที่4กันแล้วกับหัวข้อที่มีชื่อว่า The Influence of Future to Purify CoWoS AI Chipset on PCB Limited Material by Mr. Le Roux Vice President iTech Corporation ในช่วงนี้ค่ะดิฉันขอเรียนเชิญนะคะท่านขึ้นมากล่าวนะคะแล้วก็รวมไปถึงค่ะให้กับแขกผู้มีเกียรติทุกท่านนะคะได้ฟังสำหรับหัวข้อสัมมนาในช่วงนี้ค่ะ Please I would like to invite on stage please ค่ะขอเสียงปรบมือด้วยค่ะ
Hello everyone, good afternoon. My name is Ray, and on behalf of iTech Corporation Taiwan, I would like to introduce the influence of future 2.5D CoWoS AI chipsets on PCB laminate materials. So let's go started. So today we're discussing below agendas. The first one, what is CoWoS? Second, the PCB designs of different processors and applications. Third, the influence and impact on AI server PCB laminates. Fourth, development of future PCB raw materials, or we so-called PCB laminates. And the fifth, an example of AI server laminates we are using today. The first one, what is CoWoS? Why it is important to our industry? For the record, I didn't invent CoWoS. My company didn't invent CoWoS. It belongs to TSMC, Taiwan Semiconductor. And what is called is called chip on wafer on substrate. For sure, we call it CoWoS. And why people need it? You can see on the left-hand side, this is a traditional personal computer stack up. This is the interconnect of a traditional computer. From the SoC, system on chip, we so-called CPU. The signal from CPU connect to the substrate, and then going all the way from PCB, connector, DRAM module, DRAM substrate to DRAM, and going backward. This is traditional stack up. So people find out the size, the distance is too long, it's too big. So when we're doing our smartphones, when smartphone launched into the market, what we changed? We changed to POP, package on package. We put DRAM on top. We put application processors, aka processor chip, underneath the memory. We so-called POP, and we package it together. Like Qualcomm, Apple, MediaTek, people did this for 2 decades already. What's the advantage here? We can have the integration of multiple dies. We put memory close to the application processor. We also improve the performance to prevent the latency between the communication. And also we have power efficiency. The best thing is we shrink the size. We're starting from this to a small chip, 14 millimeter by 14 millimeter. Then it can be installed in our smartphone without occupying our battery space. So this is quite significant. So all the phones we carry near us to all the phones today, we're still using POP. If you got latest iPhone, you're still doing this, right? So we get the benefit of this. But this is we so-called basic chip. It's ARM-based. It's not even x86. It's not a CPU. It's not for server. It's not for AI just yet. So what can we do if we're trying to do very powerful, the power beast of the server? We do CoWoS. Why we need them? So like before, old server guys doing like this. I put on DDR4 modules. I put on so many memories, 18 gig, 32 gigs, and I put nearby my CPU doing the layout to them. We do this. But the latency here is hard to prevent. The signal integrity here through connector, through PCB is too much. You need 3 times pricey PCB, and most importantly, you just cannot power on. The signal integrity is just not enough. So let's put our high bandwidth memory, the latest technology of our memory module, just nearby our CPU or GPU. We have an interposer here, an RDL interposer, made by TSMC as well, trying to keep all the memory just next to our SoC. So the communication trip is quite short, not even reach to the substrate, and not even close to the PCB. So you from a long trip from Thailand to Hawaii just became from Bangkok to Prajnampuri. Quite closer, right? So latency here, the trip here is much, much shorter. So what benefit we can get? We can have multiple dies checked. We can have improved performance, bandwidth checked. We have power efficiency checked. We also have scalability and flexibility. How to say scalability and flexibility? If you're doing one SoC, you do all the designs, even memory combined, you need 24 months. If you put it separately and make a chiplet, you can have 12 months each, and we put it together for 6 months. You shorten 6 months from 24 to 18, or even shorter. If you have a bug in your design, you just swap the design. So if you got, for example, you got some problem for memory, you swap the memory from Micron to Samsung. Problem fixed. But if you have a design error in SoC, here, if you design everything in the system chip, I'm sorry, you have to redesign again, verification again, all over again. So chiplet, I would say, will be a very preferred solution in coming 5 to 10 years. So from this page, we see in future 5 to 10 years, we so-called AI era, chiplet, CoWoS have a very, very good preference on future structure of all the electronic platforms, including server, including we so-called AI PC, and other, so on and so on. Let's see something real. So you can see here, on the top is our hot topic, the AI chipsets. The little block here stands for memory. The central one is GPU. First generation, second generation, third generation. And it's going bigger and bigger. Second one, people not usually see it. This picture are cited from website. It's public data. It's from Apple. It's M1, M2, M3. Also, very powerful chipsets. What's the difference? One is running for data center. The other one is running for we so-called AI PC, or simply the latest MacBook, powerful one. They are so different, and they are also saying they are CoWoS. So how many CoWoS are we talking about? Because they look so different. So why are we calling the same? Here it is. From today, there are 3 different CoWoS structure. We have CoWoS S, CoWoS L, and CoWoS R. And what's the difference of them? CoWoS S is most likely the one Apple took. We put HBM dies, spare dies, inside the package with SoC. So one more time, bare dies with spare dies, and we pack together, wafer next to wafer. This is CoWoS S. You can shrink the size at the most you want, so you can put it into a laptop easily. I package together. Second one and third one, CoWoS L. I already packaged my SoC. I already packaged my HBM, high bandwidth memory, and I put on one interposer and then on substrate. So they package separately. Again, this one packaged together with bare die. This one, bare die, packaged once, bare die, packaged twice. So I put something already packaged onto the interposer I make. Not me, TSMC made. Okay, then on the substrate. And I also put IPD, LSI, and a lot of the passive components into this system to making sure the components on PCB are the minimum. So I use the most minimum space to achieve the best performance we can get today. CoWoS R also. Simply, the RDL is less. I didn't put so much component here. I didn't put so much passive here, but I put dies together to shorten the distance. So 3 different CoWoS, but one simple concept, shorten the signal distance. Okay, so let's go back to PCB. We're in THECA, so we majorly talk about PCB. What's its impact to PCB? What we are going forward in the next few years. So we just mentioned we have smartphones, we have laptop, we have high performance computing, CoWoS GPU, we have Ethernet switch. Okay, Ethernet switch is not yet doing CoWoS today, but maybe they will, in the future. So smartphone AP, we all know, starting from 2 decades ago, people are doing 2+ HDI on smartphones. And then several years ago, we are going all the way to any layer. Since 2017, the Apple company reinvented the mainboard to be MSAP HDI mainboard. Moving forward, we are seeing there are less and less space for circuit board in smartphones. So we're thinking about, can we do something ultra thin in dielectric? Can we do something ultra thin for our mainboard? For example, Apple Watch. How thin is Apple Watch? The dielectric of Apple Watch is actually under 20 micron for 1-layer dielectric. Can we do this on phone? Probably yes, but who can do it? Can you process with 13 micron core material with 17 micron prepreg? If we can do that, someday we can put into our smartphones. The final thickness is like 0.3 millimeter of a mainboard or 0.2 millimeter of a mainboard. So that's the ultimate goal for 10-layer, 12-layer. That's the ultimate goal of very thin smartphone mainboard. So in the future, your smartphone will equip with OLED display, which is already very thin, thinner than TFT LCD, and also you got thinner mainboard, then you can release huge space for your camera and battery. That's what smartphone is going to do. Second, laptop. AI PC, what is AI PC? By define, Microsoft has defined over 40 TFLOPs is the definition of AI PC, and you have to equip a key, and written in Copilot by Microsoft. And also you have to install Copilot by Microsoft. Then you are an AI PC, defined by Microsoft, making your money by Microsoft. But yeah. All right, so Microsoft has a clear definition, what is AI PC. But how to achieve the power of the requirement of AI PC? So Qualcomm find a way. So actually Qualcomm is the first one to claim they got this power horse of AI PC, and followed by Intel and AMD this May. Okay, so to support AI PC, PCB going to change as well. We didn't think about laptop PCB can be so complex. It's just 8-layer PTH, 10-layer PTH through hole. But right now we're seeing +2 HDI, +3 HDI. Also, we need some low-loss material inside to support the communication between chips to memories. And one thing very important is the laptop rigid PCB will never get too much smaller. They cannot get too much smaller. Why? The best cost efficiency design of laptop PCB, you have to have 2 ports, 2 sides of ports available on your board. And the CPU must put in the center of the laptop. This is very important. Why center? Because thermal dissipation. The CPU cannot put on each side of the laptop. It must put in the middle. So you can check all the laptop here you sell on the teardown reviews. All the CPU are mostly centered. Okay, so PCB in the center, and you need a USB port, right? I need USB-C and HDMI and USB-A on both sides. So what's the best way to connect them? One PCB, one rigid PCB. The most cost efficiency. What if I need some space? I can route my PCB to get some space. So your laptop PCB will mostly like a McDonald's. You can see from MacBook, McDonald's, the mainboard design, right? So why we are insist to using rigid board only? Because if you're using FPC, you need extra connectors. That costs money. If you're trying to do rigid flex, that costs you more money. So let's say AI PC, all the way rigid boards, more and more difficult, 2+ HDI, low loss material. That's all the way to the future. And we are seeing in 2 generations, this laptop board will be as fast as the server board today. So we are very optimistic to see the future forward for the laptop PCBs. The third one, the main topic today, HPC CoWoS GPU. It's getting more and more complex. The pin count of a CoWoS increasing rapidly. We're seeing 4,000 pins, IOs, 6,000, 10,000 pins. We're seeing more and more complex function of a CoWoS. So many pins, so many IOs, how can we let it out? We may need some HDIs. We may need some laser vias. It's not only PTH. So we're seeing 2+ HDI to 6+ HDI. Some people are already starting 8+ HDI right now. So in production, people are putting 6+ HDI in production. And I think that's where we are here, we are going tomorrow. We are going to do 6+ HDI. That's the minimum request for next year. Also, the CoWoS brings some problem to PCB as well. This is the traditional server CPU, Intel Xeon 4th generation with so-called Sapphire Rapid. The other name, maybe you're familiar more, is Eagle Stream. This is Intel Eagle Stream CPU. It's 61 millimeter by 82 millimeter. And the second one, this is the A100 NVIDIA GPU. It's 75 by 75. And the third one, this is the B200 GPU, 90 by 90. And in the near future, we're seeing 100 by 100 millimeter. Why this is important? What's the impact to PCB? The first thing, complementarity, or we so-called warpage, or people are familiar with that, is solder crack after reflow. If you got so much size here, how about the corner warpage? How can we conquer the warpage impact to the PCB? That's the first thing. Second thing, we need so many vias. Micro via is the structure we're trying to prevent for years. Sometimes we still need them, which is a little pain in the back to manufacture them to make it reliable. So how to make solder crack less, how to make laser via reliable is the next topic of laminates. For PCB, you can have you can enhance your pure strength. You can enhance your process doing laser via. In PCB, you can prevent warpage by copper ratio of every layer. You can try to balance the stack up. But ultimately, the dielectric material, we so-called CCL, laminates material you're using, the thermal expansion of it is low enough. It's also one crucial properties we are seeing here. So making sure your laminate dielectric CTE is low enough to support the stability of your AI server boards is the next big thing in AI server boards. Second, except to the warpage size things, the speed of GPU is increasing insanely. The speed we've never seen in Ethernet switch. We saw Ethernet switch, the development cycle is like 3 years, 5 years, easy. But today, AI servers, GPU servers are evolving every 6 months. From 3 to 5 years developing to 6 months, 1 year developing. That's totally changing our mindset, design our materials. Here is what it looked like when you're trying to do too much on improving materials. This is material matching with different coppers. We know material plus coppers can give you the boost on signal integrity. And this is the signal integrity, dB per inch loss at 16 gigahertz. So using better material, your performance will get better. Your loss will get less. Your signal integrity will get better. And this is, you can see this one is like middle loss, lower loss, ultra low loss, extreme low loss. But you can see the orange line here. That indicates cost. So if you are pursuing the ultimate performance here, the cost rising is not 3%, 5%. It's like 300, 400% every single level next to the one you are using. It's crazy. And right now, we are doing this in 6 months to 1 year for every new generation. This is driving our industry like never seen before. So in order to achieve what this industry needs, we have three elements of CCL laminates. The first one, resin. Second one, glass fiber. And copper foil. So we will improve in three ways, all three elements, to achieve the future requirements of AI servers. So this is resin. We're starting from phenol, ester, BZ, BMI to PPE, PPO. Some people might heard of it, which is using for like H200, like current mainstream servers. We're using PPO and PPO. In the future, we are studying hydrocarbon. There's a very good resin here, so-called PTFE, or people known as Teflon, which is not really appropriate for current AI server. Why is that? Because Teflon is not halogen-free. So in current days, all the customers we are facing, all the AI servers we are using, they all require halogen-free material. So unfortunately, even PTFE give you very good property, but due to the regulation, it cannot be applied to any of our boards. So we are sorry for them. So our development will focus on PPE, PPO, and hydrocarbon resins. Second, glass. Glass is a big thing. In laptop, no more server. Smartphone you are seeing today, we all using e-glass only, the normal glass. But for AI servers this year, last year and this year, we are seeing low decay glass, which is very premium glass, expensive and limited. But this is going to be mainstream next year. We are seeing Itobo, Asahi, Taiwan Glass. A lot of suppliers are expanding their capacity to reach the demand for tomorrow. And then, going forward, we are seeing low decay 2 glass, which give you better and better signal integrity. But Sam, they are so limited today. And we didn't see the sign to be expanded in the near future. But the bandwidths are still insanely increasing. Just like ChatGPT, they can increase their database by 10 times the next year. So our bandwidth is not enough. If we are using our old methodology, we cannot achieve the performance for tomorrow. So we are seeing the new glass. We so-called advanced low decay glass made by CoWoS. And CoWoS is another new territory to develop for all of us. The property is so good. The DF is very low, signal integrity very good, decay low enough. But how to process it? It's a very rigid. It's hard to drill. It's hard to cut. And powders flies everywhere when you process them. But performance-wise, you need it. For process-wise, you really hate it. So your plant manager might blaming you about this, but we have to do for the future. This is what we have to be done. And the last one, copper. We survey all the copper vendors, all the copper resources to find the best copper tomorrow. Here is a short list. It's like a free advertisement for the copper vendors. Yeah, I'm happy for them. So we're seeing different coppers are doing the best effort to give almost profile-free copper available on this market to prevent a skin effect. I think they are all awesome partners, and we are lucky to have them. We're seeing some success from Kotak, Mitsui, Circuit 40, and Furukawa. Also, the other one, Fukuta. So they are doing quite a good job. We are testing every one of them. So we are also making our best effort to test every one of them. So, what it looks like for actual AI server laminate. We focus on these parameters. CTE z-axis 2.0. We cannot bear too much higher than that. Like what we mentioned, this one indicates lower warpage, lower solder crack, lower delamination, better combination force. So 2.0 is the one we're working on. Decay, you cannot be too high. Higher decay, thinner trace. Thinner trace, higher loss. So decay must be low enough to prevent greater loss. Also, decay are also related to latency. Very small, but still latency will be different. So lower decay will be better. Third one, DF. DF is direct impact to the signal loss. Lower DF, lower loss. So this is three very crucial elements of the AI server laminates. Also, low etching oxidation is very important too. We tested normal etching and low etching, different chemicals, to see how many they can boost for low loss dielectrics. And some results are very impressive. At 28 gigahertz, it's below 0.8. So this is very impressive numbers, and we're really looking forward to work with all the chemical vendors here. After oxidation, you can see some colors. It's just like bare copper, almost non-etching. It provides the sufficient pure strength and combination force to the next layer, but it also without damaging too much of the surface of the copper. Make it smooth, but also cannot be delamed. The last one, how to be reliable doing AI servers. We do 9 plus 14 plus 9 sequential lamination. So it means your dielectric has to be survive under 200 Celsius for over how many times? 10 times. So 2,000 hours for I'm so sorry. Yeah, it's like 10 times, 20 hours under 200 Celsius. And once again. And also we will do reflow afterwards to making sure you can survive so much long time. As you know, epoxies, dielectrics might get degraded if you get too much thermal on it. So we have to making sure after so many times thermal, keep it so long, it can still perform just the same. And this is what we are asking for. So as you know, the latest AI server is going to do liquid cooling. And the liquid cooling might stop, might need to maintenance, or might have to shut down for a while if you got liquid cooling, your liquid plate got some problems, and your GPU might running at this temperature over 100 Celsius. And in that case, your dielectric must be very, very strong. And we're seeing the watts of the CPU, GPU is increasing rapidly. So our PCB thermal dissipation and the resistance to thermal are also very important. And one important thing is choose the right laminate with you before all the process parameter adjustment. So all of this, I think we read about today, all of this are why we need CoWoS, what's changing the PCB, and what we need to prepare to change in the material for the future. So that will be it. That's today's presentation. And thank you so much for coming and listening. Thank you.
ขอเสียงปรบมือให้กับมิสเตอร์เลรูไว President iTech Corporation Thank you ค่ะ ก็จบไปแล้วเนี่ยค่ะสำหรับหัวข้อ The Influence of Future to Purify CoWoS AI Chipset on PCB ค่ะ ซึ่งแน่นอนว่าสำหรับในหัวข้อต่อไปนะคะก็จะเป็นในช่วงเวลา 16:15 นาทีค่ะ ซึ่งทุกท่านจะได้รับฟังสำหรับหัวข้อการสัมมนาในหัวข้อ Thermal Dissipation PCB Application Solution for Power Device ค่ะ เดี๋ยวในช่วงนี้นะคะขออนุญาตให้ทุกท่านเดินเยี่ยมชมงานกันสักครู่และเดี๋ยวเรากลับมาเจอกันในช่วงเวลา 16:15 นาทีขอบคุณค่ะ